All right. Okay, and we are live. So welcome everyone to today's live stream. We are doing a life science session and a nice, interesting topic for those who are interested in quantum mechanics. We are talking about qubits in phase space and the quantum potato chip. So this is an evolving name for some interesting theory that we're looking at today. And yeah, with that, I'm going to hand it over to Nick to share his screen, but Mads is also joining us. So, Mads, if you want to say a few words to intro this idea, and then get Nick get into it.
Hey guys, thanks for having me. This has been a conversation that we had together with Nick about, what is how we can explain quantum state, classical theory, basically think about, statistical mechanics and the phase space that we have. So basically that classical theory is more convenient. And this is this approach is okay, let's treat quantum along those lines. And then let's see, if we treat it like that, how it's going to look like. So, and in particular, we are going to look into a very specific region of that space that has some interesting features. Does it going to have some very important applications? We don't know yet, to be explored and to be discovered.
Yeah, very cool.
Here's a few pictures that we generated recently, the new ones that hopefully gonna help us to understand what it is, what is this object, how we can describe it and compute it, and how to derive it from some first principles and some geometric principles and probabilistic principles, like all of that. And I think that's what we're gonna go for, right?
Mm-hmm.
So, what should we start for?
Let's start with concept of the quantum state, and the common picture, which is that sphere that we see there. People usually call it Bloch sphere. Maybe just clarifying, what is a Bloch sphere? Whenever people talking about that, it means what?
Yeah, so let's start with a simple quantum state and Bloch sphere, or Bloch plot, I guess. That's like the basic picture for the quantum state or qubit. Again, it's just representing any quantum state, two-dimensional quantum state on a Bloch sphere is just the most natural way of representing it geometrically, right? Any state, this is where the 0, 1 are the z-axis, right? There are x-axis, there are y-axis, right? So you can any random state which is pure is usually like an arrow on the surface of the sphere. Any mixed state is an arrow maybe somewhere inside the bulk of the sphere, not on the surface. There's some short, surprisingly hard to generate short arrow, but yeah, it can be arbitrary, like an arrow on the, maybe the uniform mixture is completely in the center, so it has 0 length. Okay.
And then what is interesting about Bloch vector is basically a representation in a very specific basis, which is basically identity plus polymatrices, the famous polymatrices. And then, what is special about that is that, in that very particular representation, so although you have 4 bases, for your density metrics, which is those 4 metrics I mentioned, identity and poly bases, the very first element is always 1/2. It's basically it's what I'm trying to say is, in principle, it is a 4 vector. Basically, it's a vector that has 4 elements. But since the very first one is always a constant, we just drop that, and the rest is what we see in this Bloch sphere. So this is maybe that helps. That's a good transition going from this picture to what we usually refer to as the phase space.
Yes. So this is like a straightforward way of computing the actual coordinates of the Bloch vector. Those are just projections to polymatrices, right? So polymatrices form some kind of basis, right? That you just compute your inner product of your density matrix. So density matrix is some element of some space, right? And then we just compute the inner product. In this case, is a Hilbert-Schmidt product, right? Which is just a trace of density matrix with some polymatrix. So that's essentially how we compute the coordinates of the block vector. And it can be generalized to high dimensions. Even if you generalize your Pauli matrices to high dimension, you naturally have a block vector for any quantum system in high dimensions. So that's just a way of specifying it in different space. But there's also a phase space representation of quantum systems and qubits, right? And well, we even have a block phase space representation, which essentially has coordinates, or in this case, it's just amplitudes. Right?
Mm-hmm.
So it's a special basis in which your density matrix, right? Density matrix is just 4 elements, usually just 2 by 2 matrix, but you can flatten it so that you have a vector with 4 elements. But now you can treat this vector some elements of some vector space, and you can just change its basis, transform it, linearly transform this vector into some other basis, and so on. And this phase space transformation is exactly that. Well, usually there's some I don't know, some side note that you maybe, in order to call it a phase space, the actual coordinates in that new basis has to be real, or even has to be positive, right? But anyway, it's just another basis. And well, in principle, those coordinates can still be complex, like in the original density matrix here. Let me actually show it without without any CRUD in there. Right, so the actual off-diagonal elements has some imaginary components to them usually, which are called coherences.
And by the way, like, the term that Nick used, like, flattening, like, in some literature, they call it, vectorizing density matrix. So, like, for those who are familiar with that's exactly the same concept.
I go on flattening, it's like, take this density matrix, which is dimension 2 by 2, and flatten it so that now we have a vector, which is dimensions 4. So that's why I call it flattening. But it's usually called in literature vectorizing, right? So,
and then, like, if people look at the, like, you see that line of code with the amplitudes. So what is special about, like, the representation in the normal block sphere is the first amplitude is always a constant. So that's why, like, we can have a 3-dimensional representation. Otherwise, like, because everything is in the 4 space, like, in 4-dimensional space, you cannot visualize that. And that's the headache that you are going to have. So that's the story of, like, quantum state in a phase space. So in this picture, instead of thinking about a density matrix and bunch of imaginary, like, elements, complex elements for your density matrix, you switch the gear. You would say, okay, now let's think about, like, a bunch of real numbers. So you have a 4-vector bunch of real numbers in a given space, and that's how you would describe it, exactly like that example of Bloch.
Yeah.
Then I think, like, the interesting story would be, let's impose some condition to satisfy some properties from probability theory. For example, let's say that, like, the summation of those elements is unity. So basically, like, they can be treated as some sort of probability. And if they are positive, they are literally, like, the probabilities. So that's the story of, like, phase space. So basically, like, those elements, literally you can treat them as probability vector.
Yeah, like this one. Now, well, let's just actually call it amplitudes. Those are probabilities. The probabilities, because just another special basis, which we call tetrahedron, because it has some nice correspondence in the actual tetrahedron in the language or geometric object, right? So it's like this object, right? So that these vertices correspond to exactly basis elements of that particular basis in phase space. But those probabilities in the basis actually acts as probabilities, so they sum up to 1, and they're going to be always positive for any quantum state, any qubit. So in that sense, you treat this tetrahedron as a simplex, probability simplex. So any state inside of it is an actual probability, a valid probability theory, probability vector. But not any probability vector is a valid quantum state. So it's like an additional constraint that quantum theory requires, right? And I know how we would represent this. You can represent it geometrically. You can, for the qubit at least, you can have this intuition about why it has to be constrained additionally. Because we have this picture of the block sphere, So in a way, you can think of it as soon as you have this tetrahedron, right? You can imagine, okay, what would be the maximal rotatable space inside of that tetrahedron, and that can be called a quantum state. But it only works for 2 dimensions for qubits. I don't think it works for arbitrary dimensions, so you don't have this nice geometric intuition. As soon as you have this high dimensional simplex, would any hypersphere in that space going to be a valid quantum state? And the answer is no. So it only works for qubits, but I think it's very useful to think of it in this way. It's like, okay, find the sphere inside of that tetrahedron. Maybe what is the radius like this? Oh, I have to. I forgot the radius. So there's some.
What's just square root of or go with tetrahedron and then go with the inner sphere, like that would be that's also
That's like other way around.
Yep.
Maybe. Yeah, let's just do this. You have a tetrahedron and do in sphere, right?
Yep.
So you can compute the radius. So instead of showing a sphere, just show this without thinking too much.
Yep.
Yeah, that's easier.
So basically, the tetrahedron here is like the whole let's call it simplex, or all the points that you can have if you just think them in terms of probability. Like any point there, it satisfies like those probability conditions, but not all of them represents the quantum state. If we want to put in a fancy term like any density matrix, it should be like positive semi-definite, meaning like all the measurement like they should be real values, or the eigen values they should be positive. There are many different ways of like understanding that, but anyhow we can say like not every point represents a real thing outside in real world, in the physical world. Now what we can do is like
show it explicitly, right?
Yep.
Given this tetrahedron basis, absolutely arbitrary probability vector, which we can just specify by free probabilities, because we impose the normalization by hand this way, right? So we know that we have 3 degrees of freedom to specify any probability vector. So in this basis, if you actually go back to the Hilbert space, right, to our usual representation, which we do with the Weyl transformation, right? When we do this and extract the density matrix, or maybe just compute the eigenvalues directly, we're going to have some numbers, and we can just impose that those eigenvalues has to be positive, right? Which kind of can clearly, I don't know whether you can solve it. Let's try it. Solve for.
Or we can use reduce. Maybe that's better.
Reduce for this one to be greater than 0. So what should we see? We see some kind of sort of condition, right? But this is condition in terms of probabilities, so it's not a very natural way of representing the geometry. But if you actually convert these probabilities into 3D coordinates, you're gonna see the constraint that it forms an actual sphere. And the way you can do it is, it can be done with the rotation, or we can just imagine that we can compute the block vector here, which is just xyz, right? So we can just solve for this kind of constraint. So we just form these 3 equations and solve for our probabilities. And then we just use these rules, the first solution in here. Right, this is our solution, and we solve it, use it here to compute the eigenvalues. Now we can almost, if you simplify it, sort of a minus sign for some reason. Why is there a minus sign? Well, there's I here, so I guess it's okay. So if you want to see, if you want this eigenvalue to be positive, you can see that this has to be negative in order for this eigenvalue, imaginary component, to go away, right? So and also less than 1.
That's a sphere.
Yeah, so that's essentially a sphere equations. So that's how we can derive it.
I've got a quick question there about the comment when you said in higher dimensions it's not obvious that that concept would apply. Do you have an intuition as to what makes it different at those high dimensions?
Well, I don't think I have a good definition, a good intuition either. It just doesn't work. It's just you know that the quantum theory requires for eigenvalues to be positive. That's your constraint, but it's not a very natural geometric constraint, right? It's not a natural geometric constraint if you think of them as this something inside of the simplex.
Mm-hmm.
It is something inside of the simplex, but it doesn't have like this spherical necessarily some spherical shape.
Does it still would it still be like rotational, like some kind of 4-dimensional rotation that might not be a round object?
Well, it can be rotational. If it were rotational, it would be a sphere. So, but there's no rotational symmetry. But there is some kind of constraint, at least. I think you can at least identify two spheres, like inner sphere, outer sphere, and you know that the actual shape is in between.
Okay.
So that it's just only in the qubit case, your inner sphere and outer sphere is actually the same object. So there's nothing in between. But in the high dimension, is some more complicated object. But you at least know the boundary of those objects.
Interesting.
You can compute the radius of those spheres, and the object is called qplex in high dimension. In generally,
Qplex.
Yeah.
Sounds like the title for a future stream.
Another the comment worth mentioning is that that 3-dimensional visualization in front of us. So the corner of that tetrahedron, those are basically treat them as the elements or the basis of your phase space. That's the way that you can see it. So basically when Nick is defining a quantum state, you see there the code below PQR and 1 minus them. In the tetrahedron, basically he's saying that take those the vertexes and then put those coefficients in front of them, that those are the locations that you would see on that picture.
Yeah, you can just do this. You again go to Hilbert space with the Weyl transform and compute the block vector and see it doesn't have a radius of 1. It kind of goes beyond radius 1. Now it has radius 3, right? So it's like 3 times away. I guess maybe if it's correct, let's actually see with it.
It looks right. It looks like if you just take the radius, it's like 3 times the radius.
Over here. No, it's too far away. Hold on. Oh, this because we made the in-sphere.
Yeah, radius of the sphere.
Yeah.
Well, we know the radius here, so we just scale it like this and actually use the sphere, right? And now the point is
That's the point on the top.
Yeah. Okay. So
now the other approach is if somebody think about okay, let's if it's if it's pure probability vector, how it is typically called in the literature, that very specific basis and the corresponding description. So this is the story of positive operator valued measures, POVMs. Okay, so here we are talking about POVMs. That tetrahedron is basically a specific basis representing a very particular POVM. And then you have infinite freedom, how many POVMs you want to pick and what you want to do with them. And of course, somebody can ask, what are the optimal way of, doing that? What is the best way of picking those POVMs? One feature that is very interesting is that we can say, let's go after POVMs that are informationally complete. Basically, minimum number of POVMs that we can pick in order to expand the whole space. So that's the story of in that abbreviation, IC in front of POVM. That's the story of informationally complete. Okay, which trivially one can see there are 4. Okay, so it's basically whatever is your dimension, the square of that is basically 4. If you impose a condition, etc., you can say it's d square minus 1, but let's not impose that condition for now. And then you can add other features. You can say okay, I'm gonna look for some very specific ones that has some interesting feature for optimal calculation. You can ask them to be symmetric, etc. And that's the story of that S. And using our friends Chris Fox SICK POVM, that's how we can call it. So the way that to pronounce it is basically SEEK, so SIG POVM. That's the story of like, you know, those bases and like, you know, the space that we are describing.
Yeah. And that's the relationship. So you have some measurement operator, which is just a way to measure your quantum states to get some probabilities, right? In this case, you get, because you're measuring in 4 different bases, you get 4 different values, right? And each of them has the corresponding probability. And another way of thinking about the same computation is to do the basis transformation in phase space and that of your quantum state, and you get your amplitudes there. So either you have an amplitude in phase space, or either you measure with this SIG POVM measurement, you get the same values. So that's the relationship. They correspond exactly, right?
And they're one-to-one correspondence, like, you know, with the experiment. Like, and again, like, you know, you look at those 2 lines of code. One of them represents a measurement. So it's like literally you do a measurement, these are the probabilities that you get. The other one is your probability vector. That's, call it state vector. Now it's a state vector in a phase space. Okay, so that's how you can get it. One thing is that, like, you know, I know typically people who know quantum, whenever they think about measurement, they always have projective measurement in their minds, which means, like, you know, the states that we have, they are orthogonal. Keep that in mind. Like, you know, when we talk about these POVMs, you know, the corresponding states, they are not orthogonal. Okay, so it's just a completely different picture.
Well, we can
just to
actually show them, right? We can.
Yes, let's show, like, you know, the states in the block sphere, like, you know, just to clarify that.
Element. So yeah, so if you just extract the actual elements of that measurement that correspond to each of those elements that you're measuring, or you can turn them into quantum state, because they're just 2x2 density matrices, right? And maybe extract the block vector. And you can plot those, or, well, without plotting them, just computing the norm. It should be simplified. So for the tetrahedron, it's just a squished version of, it's like lives inside the block sphere, right? It's just halfway through, right in the middle. For some different SIGs, there may be different.
Show them, like, you know, actually, like, you know, Nick, you know, instead of just showing norm, let's show those points directly inside the block sphere.
Yeah.
So, like, you know, you can make them rapid as points and then graphics. Yeah.
Yeah. I'll just show plot for this one.
While you're doing that, SIG POVM, is that the acronym for symmetric, informationally complete, positive operator valued measurables?
Yes.
Okay.
My mouthful, yeah, I know. Okay, I show it like this.
Yeah. And this is, like, you know, this is a subtlety that like, you know, I want, like, you know, audience to pay attention. Like, you know, the basis, like, you know, in terms of basis that we have now, like, you know, Nick is showing, like, you know, let's adjust the opacity. So the basis is that big tetrahedron that kind of, like, you know, everything is trapped inside. Okay, so that's your space. With the basis are those 4 corners. Okay, then the quantum one is, like, you know, the sphere inside that's the only region that represents a real quantum state. And then the POVM elements, they live inside that because they correspond to a real physical system. So it's just, it's a subtlety, like, you know, one can say, oh, it's just, like, you know, rescaling. Yes, in a sense, like, you know, in this spatial case, it's rescaling, but this subtlety is very important. Like, you know, the big one is your whole space, and then POVMs always lives inside that is in a sphere, which are quantum.
Is the way to say that, in layman's terms, maybe that in reality, what is probable is only a very small subset of all possible probabilities?
That's basically exactly what we are saying. Basically, it's like, you know, this is the story that we would say it is as if you are generalizing, like, you know, this probability game that we have in quantum, it doesn't cover the whole space. It just covers a specific region of that. And of course, a very interesting question is why it doesn't cover everything. But that's one way of thinking about that.
I think that rotational idea kind of appeals to me there. It's like it's the only space that allows it to come in from any angle, sort of thing. And later, yeah, there's some other interesting shapes that have a similar feel to it. The fact that it's like rotationally symmetrical or something. A question about that.
Why you have...
Yeah.
Question. Okay. Well, I was going to say just the rotation is because we have unitary transformations, unitary gates in quantum theory. And those usually are just are thought of as some rotation, right? You can always, for qubits, you can always make a correspondence of the unitary gate with some 3D rotation, right? For high dimensional Hilbert spaces, you can also do the same correspondence. So essentially, you already know that what you do when you apply some unitary transformation, you rotate your Hilbert space, right? So that's why this requirement feels very natural. So that you have to have some sort of rotational symmetry, maybe not completely, but at least somehow bounded, so that you can freely rotate it and don't go beyond the probability simplex. You can rotate your actual state arbitrarily.
And this line of research is also very interesting because there are two ways to think about, like, okay, how we can explain quantum from a more fundamental theory. One approach is like, people like, historically they had this idea of like, okay, like, whatever is quantum theory, it is some form of, non-commuting, generalization of probability theory. Okay, that was the general approach, which was highly motivated by Hilbert space structure, tensor product, etc., etc. So that was the idea. This approach is like, it's the reverse. So basically in this approach, you think about like, okay, that phase space, and now there is a restriction on the standard, like, probabilistic case. Like, it's like you're imposing some restriction, literally like, the picture that we have there, like why only like, that is sphere. And then you can ask like, more interesting question, which is the story of like, potato chip. You would say, okay, so now here you're telling me like, I have like, those variables P, Q, and R, and like, I can describe that. Now, is it possible to reduce the dimension one more? Like, instead of that, like, what would be more minimal description of like, this probabilistic case? And if you go one step down, it's like, you would say, let's say that like, you have a 4-dimensional geometry, and you would say, which part of that geometry I can describe by just 2 lines. Okay, you would say like, I have only 2 lines. These 2 lines are the most minimal descriptions. And by some like, the geometric, play of these lines, which part of this space I can cover. So that's basically like, the story of like, quantum potato chip. Like, you start
maybe we can like a bit make this transition more smoothly by just first start with an actual what this means to have a projective measurement.
Okay.
Right? It's like we just explained like this. It's like we're going in reverse, right? We kind of introduced more complicated measurement object, like making POVM and making the complete measurements. But the actual usual way of doing measurements is actually doing some kind of projections. Like you have a qubit which acts as a polarization or spin or 2 energy system, and you want to project it to actually measure probabilities being on one or another. So we just have 2 alternatives. Usually it's like spin up, spin down, spin left, spin up, energy 1, energy, and like ground level, excited level, all this kind of quantum systems. You just have 2 values, but that's why it's a 2-dimensional quantum system. So usually we just project to some kind of axis in the block sphere. So you pick the axis, like the z-axis, and you want to see whether your actual state, what is the the projection, and how this projects it, and how far away it's from the actual like those basis elements. It's actually up, or actually down. So depends how far away you are. You can measure the probability, right? So that's how we do the projective measurement. This is literally just, okay, we have now a qubit, you measure it in Z basis, you get 2 probabilities, you measure it in X basis, which is just a orthogonal direction for your spin, for example. You get some other probabilities, but those are binary probabilities, right? So those correspond to just access. But in the context that we just described, right, those two binary access, they represent like some independent probabilities, right? But in the complete picture, when you have this POVM with 4-dimensional probability basis, it kind of acts as a joint probability distribution of 4 different values. So and this way, it's a natural way to ask whether for what states you can get this probability vector, 4-dimensional probability vector, just out of those two. Essentially,
Actually, like,
the same as asking when those are independent.
Nick, go back to those projective measurements, show the corresponding probabilities. Basically, what Nick is saying is, let's say that you're an experimentalist, you perform a measurement, you get these two numbers, and then you pick a different direction, you get these two numbers. And then somebody asks you, can you tell me what was the quantum state? Sadly, the answer is no. Okay, so in order to reconstruct, that's the story of quantum tomography, etc. You have to do much more in order to construct your quantum state. Okay, so by just doing these two measurements, you cannot do that.
Yeah, essentially you're constraining. It's like you can think of it. Okay, you have this x-axis, z-axis, and you know how your quantum state projects on both of those axes. So essentially, you only know the line. Right, yep. You only know on which line you can isolate the line where the state belongs to, but not exactly what it is. So we need at least one additional projective measurement in order to determine what it is.
Having said that, the interesting part about POVM, but there you have to do 4 measurements, is that with that result, you have full construction of your quantum state, because once you have the probability vector, you know what is your quantum state. Okay, so these two are kind of the interesting feature of POVM versus projective case, which is the case that Nick just described. Now,
it's the story of 4 measurements, right? It's like how to construct a single measurement that has 4 outcomes. I don't even know how to do it experimentally. It's like how directly measure the POVM in this case, how people actually do it.
Now, then the story is now I think we are trying to clarify the motivation, when we talk about why this is interesting, because you want to say, okay, which part of your state space can be reconstructed fully if you only have those 2 projective measurements? Which is an interesting question. Can it be an interesting resource for quantum computing? We don't know yet. Okay, so there are many interesting questions they can ask, what is the spatial about? What is the magic about these states? But we don't know. But we can ask this question, let's say if I only give you these 2 measurement outcomes, how would you construct? Is it possible to construct your quantum state? Typically, scientists, physicists, the first response is no, you cannot do that. But the true answer is yes. There is a very spatial region of your Bloch sphere that you can do that. And that spatial region, it has a very interesting, geometric, description, which is basically the shape of that. That's why we call it quantum potato chip. It looks like a potato chip.
Looks like a Pringle, right?
Yeah.
But that's a brand name, so we're just going to call it the generic potato chip.
Yeah. But the way, it's maybe Nick, if you scroll down, there should be another picture there, yes, this one, this is literally the way that you can construct that. So you see that line, the blue line, that's basically your one simplex. This is just a line, and you pick randomly 2 points from that line. You can call them 2 points, I don't know, whatever. If one of them is going to be P1 minus P, the other one is going to Q1 minus Q, because the summation along that line is always 1. So you have 2 points. And then what you would do is just you would say, okay, let me just get the Kronecker product of these 2, and let's just flatten that for the sake of just having a vector of 4 elements.
Yeah. So that's
Okay. So
that's a
so
pretty
so far, I
special
feel like we are not doing anything strange. Like we are just saying that what if it was possible to do that? Okay, it's just like we are using the most simplistic description that we can have. Okay.
Yeah.
Now that
Essentially, we're just constructing a joint probability table, like
Mhm.
given two like fair coins with probability P rounding heads and another with probability Q rounding heads. The joint probability table is going to be just this chronicle product of those two. It's like this is essentially saying what is the probability of both of them landing heads. This is the probability of one of them landing heads, another one tails, and so on, right?
Mhm.
So that's just a natural way to make a joint probability distribution over two small ones.
Yeah.
And they're
Keep that in
independent.
keep that in mind, like the last result that you see here, that vectorize state vector, that lives in a very generic simplex in 4 dimension. That's basically simplex 4. That's basically your full description. Like basically, if you think about like a probability vector that has 4 elements, sorry, it's a 3 simplex. So
Okay, kind of.
no, what the
It's a proof
convention
of
for K simplex, does it mean it lives in K plus 1? Now I'm forgetting the convention. But in Wolfram language, it's going to be simplex 4 or simplex identity matrix 4. That's basically your full space. Actually, it's nice to show that region because the embedding and geometric dimension, it has some interesting features. So let's go with the simplex 4.
Well, you can't really show it. So
Just wrap it as a region just to show the the embedding. You see, this is the trick. So you would say, okay, if it is truly a geometric, object of dimension 3, there should be some fancy way of projecting that back to 3D. Like that's our attempt to visualize that. And I guess our audience, they already guess how it's gonna look like eventually. It's gonna be tetrahedron at the end. Okay,
well,
so
you can visualize it like in lower 1 dimension lower. It's just now you're treating, let's say you don't have a tetrahedron, now you just have a triangle embedded in 3D. So it's a 2-dimensional shape embedded in 3 dimensions, right? And one way of actually projecting it to a lower dimensional shape in actual 2D, you can just perform some rotations. So you just take this identity matrix, which is just unitary, this unit vectors in the corners of that triangle. You can just rotate it by essentially like vector 1, 1, 1, which just goes through the center of that triangle in the direction of one of the axes, maybe z axis, right? You rotate this identity matrix. Now it's some other vector, right? Where the last coordinate is the same. So essentially we just rotated it. Let's actually show. Looks like. Now it looks like this. Together with the original one. Now we're just doing geometry live. Right, so we just rotated it like this. And now we can just splat it down to the ground or just throw away the third coordinate, the z-axis. And now we have a 2D shape, right? So you can do just that. This is our 3D rotated, and we can just do most of it, which is just throw away this last coordinate one. And now we just have 2D points, 3 2D points. So that now we can use graphics instead of graphics 3D. We just wrap it with point. Now we have these 3 points to make a triangle. Does the simplex work? Like this? Whatever.
Wait, are you saying that that's the same as the top view? Like, are you projecting down?
Yeah, it's like top view.
So Nick is translation transform, I put in the Zoom chat in case. Like that's basically translation transform, just z -1 over square root of 3.
Yeah, you can always do. But you still have to throw away the coordinate in order to show the graphics. You have to make 2D points. But if you, in addition to this rotation, you also do the translation. It just sets it to 0. Right? You can just throw it away. So in a way, this is just the top-down view or bottom-up. It depends. It's like where it's X and Y.
I would say add it there, like, add another, like, in that graphic 3D, also add the translation. So they would see rotation and then translation, bring it down into the,
Right. So we have the third simplex, which just this one.
Yes. Okay. This is what we are talking about.
Yeah. And I'll do it in one dimension higher. So that's how we essentially make a qubit or a simplex or probability space for a qubit. So that now you have a tetrahedron embedded in 4-dimension, you rotate it, and then just throw away or project it to a 3-dimensional space. That's how you get this tetrahedron or this tetrahedron. This is actually a bit different. If you notice, this is like a slightly flatter rotated tube. So there are maybe 2 different versions of those that you can construct. I don't know whether I should explain it or not. This is like, you see, this tetrahedron kind of actually has some sphere is poking outside of it, right? But this tetrahedron has a sphere exactly inside of it, so it's an infinite sphere.
But wait, Nikolay, I have a suggestion here. Like, let's make sure that, like, we explain the graphic below when the tetrahedron has the whole sphere. So basically, let's make sure it's clear. So you saw the process, that surface that you guys see, that surface is literally like, that Kronecker product. Like, it's literally like, just say, okay, I have that Kronecker product. But that Kronecker product, where was it? Like, if you scroll down, Nick, there should be somewhere there. Yes. So you see, like, somebody would say, oh, hold on a second. This is like, 4 elements. I cannot visualize it in 3D. So you just need to add, like, rotation, right? Like, that rotation is going to bring it down to basically call it, and then if you just simplify that, you see, through this particular rotation, the first element will be always 1/2. Very similar to the example that Nick showed, like, you remember, like, the last element was 0 here, exactly this example. You see, when it's constant, you can just say, okay, I can ignore it. This is reduction in dimension. You go from a higher dimension to a lower dimension. And by the way, keep that in mind. This is happening in the probability space. So we can get that one, and then, like, we can just visualize that surface, and that surface is literally the picture that you guys saw above. Yes. Yeah. This is basically like, and as you see, I guess people, they can also see the simplex, like, in case we can, I don't know, Nick, do you want to show what happens to the simplex after that rotation? Or, it's interesting, but in case.
Yeah, we can do, well, I don't know what, is it just to just show tetrahedron or simplex? Is it identity matrix with some 111 appended to it with Haki?
No, it has, like, it's a bit more complicated than that. So if you want, you should add that rotation transformation on simplex 4. That's basically the same process. Add it on, applied on the simplex 4 only.
No, the identity matrix essentially.
Oh yeah, and then drop the first elements, and then wrap it as a simplex. That's a simplex. That's a new tetrahedron that we have. Yes, you see here, like, now. Let's see. So let's just understand it one more time. The simplex, the tetrahedron that you guys are seeing here, is a projection of that simplex in higher dimension into 3 dimension. Okay, it's just like, we just rotate it in a particular way that the first elements are always constant, and then we just drop them. And this particular surface is the only part of this simplex, this tetrahedron, that has that particular feature. It can be reduced to yet a lower dimension, which is that Kronecker product that Nick was showing you there.
so that now we can think of it as a two independent 1D simplices.
Yeah.
Just the product of those. A joint distribution of two independent coins, if you wish.
Can you make this?
So this is an algebraic submanifold of the probability space, which is itself a tetrahedron in 4 dimensions.
Yeah.
And the property that this highlights is the space of probability amplitudes that have the feature that you can know them by just one projection.
Well, it's not amplitudes. It's just we're not even talking about quantum, right? So we can code them probabilities. We have a probability vector living in 4-dimensional space, right? Because it has 3 degrees of freedom, we can project it to 3D. That's the shape you get. You can also ask the shape. What would be the shape, the subshape of that corresponds to probability vector of 2 independent coins?
Yep.
That
Up here, nothing is quantum. Like, it's like it has no reference to any quantum theory. It's just pure probabilities, like, reducing that.
Okay, so this is.
Can you make this a bit bigger?
No,
I just
it's like
drag the image a bit more.
So it's 4 independent variables that are all intertwined. They sum to 1, and they live on this manifold, and they can be treated as 2 independent coins.
So, can I try to draw something on top of this, which is my trying to understand interpretation? So if you keep that still, just drag it a bit more to the right. I want to see both of the edges.
What?
I want to see the back edge as well. There.
So
okay, stop
maybe
right
Nick,
there.
Play with the opacity, maybe the opacity of tetrahedron and the opacity of that surface, and maybe removing mesh. It's gonna help more.
Maybe,
Okay,
well,
so,
I don't know.
Okay, just keep it right there. Let me try to figure out something here. So if we say these are 2 independent coins, right? So maybe there's something like this is the one probability direction. This is another one over here. So there's like a line here, and then this is going that way. But these are kind of orthogonal in a way. So what happens is if you start here and you follow this line all the way
parallel. Those look like parallel to me. If you pick like you pick this one and this one.
No, this one here at the back.
Orthogonal.
This.
Well, this one on the back, they kind of parallel. If you just take this shape and squash it down to a surface, that would be just parallel.
If you squash it down to I'm pretty sure those are opposite like that. Isn't that the tetrahedron? It's this line here at the back and this line here in the front. If you spin it in that direction. So anyway, my point is if you follow these lines, if you follow this line all the way through here, it's going to end up at this line here, right? And then as you move one block at a time, you're basically progressing here in proportion to how much you're progressing down this direction. So in a way, this is the only shape that can exist where every time you move orthogonally here, you have to move orthogonally here. And it's the way to keep things 100% orthogonal. If it was any other shape, then there would be like a preference to go in like more here or something. That's the way I'm feeling of it. So it's like the independence of the coins. So regardless of what you do with one, the other one will always be completely independent probabilistically. That's kind of my sort of interpretation.
Well, let me try it. So let me try myself then, right? It's like if this is your one-dimensional simplex, right, corresponding to like p 1 minus p, so it's one coin, right? Then this one is another coin. Okay. It's like q and 1 minus q. And for example, if you start from the most maximal state when you have determinate coin that always lands heads, for example, if you want to just slowly moving one of the coins, just changing its basis, whether it's like towards a coin like tails or heads, you can only draw a straight line. So in a way, especially this is like hyperboloid shape is made out of straight lines. So that's like
yeah.
a geometric intuition about it. You're just moving and rotating the same simplex so that it has to be living inside this tetrahedron, but it's always moving one single straight line across it.
That makes sense. So yeah, so if you're trying to draw lines directly across, let me bring out my little pen here as well. If you're trying to draw a line directly across like this, it's always going to be a hyperbole. There's no straight line that gives you a correspondence like that. You have to go, it has to be through a curve. The straight lines are only going away. Something like that. This is the geometric interpretation. What do you think, Dugan?
Yeah, I mean, it's a ruled surface, so the straight lines there are two families of straight lines, and they're going at angles that are sort of. I mean,
But
are
you
they?
can span the whole surface with just one line. It's like you imagine that you just vary P or Q in that tensor product, right? In this Kronecker product, you just vary P. It's like moving across this edge of the tetrahedron, and you want to draw a straight line because everything is linear. We're just dealing with linear transformation. So the straight line always has to go into straight line, and it has to just be connected to this other side of the tetrahedron. You can just compute it, right? And you just only have one way of drawing that straight line. And the surface you get when you just connect all of those straight lines is this one.
Okay. So it's the other side of the coin, basically. Yeah. Because every coin that you flip, it has to be one side or the other. That's what the straight lines are. But it's the disconnected coin can be it could be in either direction.
Yeah. So in a way, yes. But something like that. Maybe.
Is it resonating, Mads, or what are you thinking here?
Actually, like, I never thought about, like, how we can interpret this geometric region from a probability theory approach. Of course, pure mathematics, one can say, oh, it's only the Kronecker product and then, rotation, which is a very bad explanation because it's just phrasing mathematics in words. That's not an explanation.
Yeah.
I know many scientists, they do that. The moment that you explain like a complicated thing, just rephrase mathematics in words.
Yeah. I'm really thinking about like
I don't have a good answer yet.
Like how to... yeah.
But one thing is clear, like, this surface that you see, like, you can do some, balancing with that. Like, it's there is not the only surface of that particular structure. So there are two more surface very similar to that, like, exactly the same. It's just like, a geometric transformation of that. So you see, like, for example, this shape is facing this way, like, then you have like, two other faces but anyhow, like, let's not make it more complicated. What I'm trying to say is, like, there are some transformation that you can play around that, and like, you can get other surfaces.
Yeah, I think it boils down to because you have 3 different ways of picking, of representing this probability vector given this 2, because like it's like how many ways you can pick 2 pairs out of 4 elements. So you have 3 combinations. So you can, and that will get 3 surfaces like that. And I have the potato version of those, I think, because okay, from this picture to potato chip now is straightforward. You just cut it out with the sphere, right? Where picture here, just cut it out. But if you do it for 3 of those, for 3 different combinations, you get 3 potato chips like this. That's kind of another nice picture.
So is that what you were saying, Matt? Those are the 3 different ways to use.
Yeah.
So basically, like, if you, Nick, scroll up to that picture that, like, that we had this sphere, the one above. So this is quantum. Okay, so this is the thing that, like, it's just adding that the sphere is a feature coming from quantum. Okay, so here, like, it's a constraint that comes from quantum theory. It's is it possible to reduce it into some, like, probability theory features? I don't know yet. Okay, I don't have any explanation. I like that you know the kind of like hypothesis that like if you want to pick an object inside that tetrahedron that is the most symmetric, definitely it's gonna be that sphere, but it's
No,
not.
I think there's a you can explain it in terms of projective measurements again, because those are exactly those, like two of those make the whole sphere, right? Well,
No,
not
what I meant was that like why a sphere? Like because we
Yeah.
know that in higher dimension it's not a sphere. It's not like a generalized sphere. So that case we don't know yet.
Actually,
So
what
basically
Nick
this feet.
what Nick
But you
said
can
now
still
makes a lot of
decompose it,
sense. Yeah. So in other words,
like
I might be interpreting it wrong. Please continue, Nick.
I mean, like given like arbitrary vector like this, right? Arbitrary probability vector, you can still try to decompose it as some kind of tensor product, maybe mixed one. If you it's like if you don't ask whether you just enough to have two coins, but maybe it's some mixed combination of coins, right? You can ask this kind of question. So there's still some correlation involved. But then you can ask, what in what sense those still gonna contain some. Well, it has to do with this. It has to do with actual positive observables in the end. You just have to formulate it how you can derive these observables purely from this probabilistic perspective. So it's not maybe so clear, but there has to be a way.
I've got a question. If you go back to the SICK POVM, that's a tetrahedron within the sphere. So if you look at what that shape of the Pringle is cut out from that SICK POVM, what would that look like? Would it just, but it's the same angle, so it'll just go back to the original. No, it won't, because it's a smaller space.
Well, you can do it technically. I don't know what's the point of that.
Actually, my original question was the angle of that POVM there. Is it important? The fact that they line up with the points of the ultimate probability set? Or can that actually be...
Because they're just linearly related. It doesn't have to be purely scaling.
Mm-hmm.
But technically, yeah, the way you usually, if you have a POVM, you can turn it into a basis, right? Yeah. There's just a mathematical procedure of how one go from one to another. So it's just, for SICK POVM, it's just a very simple looking thing in the end. It's just a rescaling. For arbitrary POVM that is not symmetrical, maybe it's not something more complicated than just scaling it up or down.
Okay.
But yeah.
Okay, so that inner tetrahedron can touch the inner sphere and it will still be a POVM. Like, is the size important, was my question.
I think yes, it is important because there's some normalization condition that POVM has to be satisfied. Because it itself has to act as a probability in some sense. In this case, it's like if you sum up all the vertices, their corresponding density matrices in that case. You think of them as quantum objects. If you sum them up, they have to produce identity.
Yes.
It's like, so they act as probabilities, but you work with them as density matrices, right? So they, instead of summing up to one, they sum up to density matrix, to identity matrix. So that's the condition that POVM has to satisfy.
So can we put that into the end picture where it's actually part of the potato chip?
Like this one, or this? Well, we can do this one.
We have one in let's see. In the draft that we are preparing, Nick, we have one of them, like the potato chip, and then like the cubism SICK POVM points. That green tetrahedron.
Oh, I see. Where is it? Oh, that's cool. Yeah. This one.
Yes.
Let me find the code for it. Though it's kind of ugly as a picture.
The code should be also there. It has...
Yeah, I'm just getting it. Hold on.
Maybe it's worth mentioning for our audience, like when we this should be like insufficient. Yes. when we were exploring these problems only in the environment of a Wolfram notebook, then our narrative, the way that we were understanding that, was utterly different when we decided to go into a different platform, such as, I don't know, a PDF. Let's tell the same story, but in a PDF environment. You'll be surprised how much your storytelling is limited by the platform that you pick in order to tell that story. But yeah, like that's a topic for another time. Like, you know, how we communicate and how we disseminate science, like, you know, and many scientists, they don't pay attention. Like, you know, it's, at least for computational sciences, gosh, like, you know, PDF is not my favorite. That's
well, especially when it comes to geometry, I think that's like a huge drawback.
Yeah.
The fact that you can spin these things around is awesome.
Like, you have to like produce multiple pictures from different perspectives in order to actually see it.
Now, for example, like, you see here, you have an interesting freedom, right? Like, you know, for example, when you look around, like, you know, some people, they may notice something. They may say that, oh, look at, for example, like, Nick, turn it such a way that we see Q1 and Q4 bare.
It's a
right?
square,
like, you know,
basically.
maybe I would say, oh, interesting. Look at Q1, Q4. The middle point is going through that axis connecting, like, you know, L and R, right? That is an interesting feature. It's literally like, you know, if you create a new POVM like that, you say, okay, let me add up Q1 and Q4. Let's create a new one. This new POVM is going to be literally along that axis. Of course, it's not going to be at the pole. It's not going to be projective. It's going to be something in the middle. Yeah. And you can do the same if you play around, for example, Q1 and Q2 the same, Q1, Q3 the same. So basically now here you have 3 new choices. Instead of going with these points, Q1, Q2, Q3, you can say, let me consider a combination of Q1 and Q2. It's going to be polymetric Z. You see here, like, you know, it's 0 and 1. Then Q1, Q4 is going to be polymetrics Y. Q1, Q3 is going to be polymetrics X. And that's how you can go toward projective measurement.
Well, it's they're kind of symmetric, right? It's for a reason. Yes. It's called symmetric. It's like you can think of it as essentially the way you go from this POVM to the projective measurements. They like somehow identifying some of the measurements. For example, if you want to measure the projective measurement along the Z-axis, somewhat you just identifying Q1 and Q2 and Q3 with Q4. They kind of be collapsed because their average lies exactly on that axis. So you just identify them. So in a way, you say when you do the projective measurement, you stop distinguishing between those. You're kind of throwing away the information into the environment. But that's how the entropy increases when you do the projective measurement. Because you identifying some of the actual results.
But there is like a minor difference compared to projective, because the average of, for example, Q1 and Q2, you see it's a point in the middle of, like, you know, that axis. It's not exactly at the pole, right? So this is basically like, you know, right now we are calling that some sort of shrinking. So the result that you get from this POVM is a bit smaller than projective, because you see, look at just the position. It's inside of the sphere. It's not at the surface of that sphere.
Yeah, that's actually such a good point. It's a shrinking between, if you look at Q, okay, let me bring up my little pen here. Green is probably the wrong color for this one. Let me use pink. Okay, so if you look at this line coming down here, it's going to the center, right? It's touching this kind of like square surface of the potato chip within the inner tetrahedron. It's touching at this point, and it's touching at this point. But it's kind of trying to get to this in a shrinked manner. Do you know what I mean? But it's not quite. So there's kind of like a soap bubble effect to that point. But it has to touch at each of these points there.
And then, like, you know, the next step would be, I don't know, like, you know, how easy is to explain that. Like, you know, Nick, do you want to create those POVMs and see how from their projective plus shrinking, we can get like, you know, the original result.
Yeah, actually, change that. Can you change the angle a little bit to line up one of the Pringle edges with one of the green dots? I just want to see how close it gets if you project this Q out here. No, it's kind of off, right? It doesn't get...
So the peaks and the troughs of the red thing, of the red curve, like if you look down Q1 through Q4, it should be in line with those red peaks.
Oh, yeah, yeah. Something like that.
Peaks, I mean.
Yeah.
Yeah.
Mhm.
Yeah.
It's actually
and
not.
Same would be true for the. Q2,
It's actually
Q3.
not in the dead center there, which is interesting. Can you see that?
Yep, it has a belly. Yep.
Okay, so then my theory was wrong.
Huh.
Or was it just the
Well,
angle?
I mean, that was
Oh no,
my
there it
theory,
is.
but-
Yeah,
the,
no.
the chip,
Yeah, it
no,
is.
the
No.
chip is the center. The center is on the potato chip, definitely.
Yeah, yeah.
I think it's a parallax.
Yeah.
It's not. If it doesn't look aligned, it's.
It was very cool.
I think they are aligned anyway.
Anyway.
Yeah, so that's,
So-
I mean, yeah, it's interesting. It's like, what does this mean though? The fact that these things are all, it's kind of like this is the only, yeah, what does it mean for our lives when we flipping points? that's what I'm curious about. Geometric
Maybe it
intuition.
also has to do that it's like the probabilities are always convex, so they have to be somehow contained in the convex shape.
Mm-hmm.
Right? You just connect some points together. Maybe that's how.
So it's this reduction and these probability things that you have. You have these 4 coins essentially, and they have different weights. So each point in the tetrahedron is assigning different weights to these things. If you know 3 weights, you know the 4th because all the probabilities have to add to 1. No, it's
Well, when you think
wait,
about
no, it's
weights,
a 4-sided coin, right? With these.
You have to think about bases. Like if you actually want to present it as some kind of weights, you have to think of in terms of these basis points, not the POVM points. POVM is maybe by itself it's a bit confusing. It's like this is the
Yeah, because the that's just the actual results of flipping the 2 coins, but the sphere is the possibility of like kind of like quantum versions of that, where you flip the coin and you haven't flipped the coin and yet, or something like that. It's kind of like a
Well, okay,
it's
so
like an imaginary
if you have a coin, if you have a
measurement.
coin with 3 sides to it, so it's kind of like a football with flat, like triangular,
so
and but basically one of the sides had 0 probability of landing. Then really it's just a probability split between the other 2. So you don't have to think about it like a 3-sided dice, a 3-sided coin, or a weird football or whatever. You could just think of it like a coin. So like algebraically, it's like you have this thing with 3 outputs, but one of the outputs doesn't matter. So you can think of it like something with 2 outputs. And here it's doing the same thing, but it's saying one thing with 4 outputs, but somehow you can think of it like 2 coins being flipped.
Mm-hmm.
I don't know what you're trying to.
I think we need.
It's
I
like
think we need a
you can
picture.
go like. I mean, it's like you.
Or you have you have like this weird
this is
4-sided type of dice, I guess, like a tetrahedral dice, but the weighting on the probabilities is such that it is equivalent to 2 independent 2-sided dice of
Yes.
some probability weight
for the potato chip, yeah.
for the potato chip.
Mm-hmm.
Actually, what happens when you flip a potato chip? acts the same as a coin, right?
Mhm.
Okay.
Anyway, like it's maybe I have another meeting in about 10 minutes. I would love us to also briefly discuss the other, Nick, if you scroll down, the one that you have for other type of, this picture. At least let us briefly mention, like, what is this picture? Like, you remember, like, in the case of SIG POVM, that tetrahedron, it was basically containing your Bloch sphere, okay? Like, everything was inside that tetrahedron. It's because, like, those SIG POVMs, like, not only you have the summation of, like, probabilities equal 1, each single term of your state vector is also positive. Historically, like, before the SIG POVM, like, scientists, like, they were talking, whenever they talk about quantum in phase space, they had other ideas in their mind, mostly like, Wigner representation of quantum states. And in that representation, everything works fine with one caveat, and that caveat maybe is a very strong, like, thing. It tells you that your state vector, the terms, they can be negative. So this is what usually people call quasi-probability, okay? And it's like, like there has been lots of discussion about, like, okay, like, how to interpret that, etc. Like many assumptions, like, in classical probability theory, it's still applicable. You can derive lots of interesting things, but the price that you're paying is going from, like, probability to quasi-probability, okay? So if you go to quasi-probability, there is this thing. So, like, there are some cases that are beyond that simplex that we had. Meaning, if you enforce only positivity, the tetrahedron that you are getting is not going to contain your Bloch sphere. And which is exactly like, the picture that we are seeing here.
Yeah, so basically the points outside of the tetrahedron, those are the points that have negative probabilities. They're still valid quantum states because they live on the Bloch sphere, but because they're outside of this particular tetrahedron that we chose, they're going to have negative probabilities. That's why we call it quasi-probabilities. So it's just a bad choice of tetrahedron, essentially, because it doesn't enclose our quantum states completely. So it's like the same way of saying that we chose a bad test suit for our quantum states. We're asking bad questions, so that's why we're ending up with negative probabilities.
So how did they get to this size of this tetrahedron then in the first place? Is there some natural way that they thought that would make sense?
It is natural in the common sense. Now there's no like different shrinking involved in order to compute projective measurement probabilities. It's like you can just, like, when you do this, if you take this random quantum state and you measure it in the usual sense, like in z direction, right, you get some probabilities. How you can recover it from these probabilities is straightforward. You just add them together. It's like, take this number, add this number. I think you get this number, if I'm not mistaken. Okay.
Yep.
So this is like this table that you can get. I think you can also get it by prime quasi-probability, we call it. Right. You get this table, right? This is now a quasi-joint probability distribution, but now you can just, by itself, it has some negative probabilities, but when you sum them over, you always get positive results. So this corresponds to exactly some probabilities.
Now, if you add up the columns, these are the projective measurements along z direction. Now, Nick showed the probabilities in x. Now, if they add them up, like, along the rows, it's going to be the probabilities that you get along, like, x direction.
So does that mean the area of the sphere and the tetrahedron here are the same? The volume. So
not the area.
Not the area of the volume.
I'm not sure, actually. No, I doubted that it's like there's going to be some kind of pi. No, the volume is not the same, but
is there a way to calculate that easily? Or is that a complicated thing to do?
No, it's well, if you have a unit sphere, right? It has a straightforward volume. Hold on. What? Is it undefined? It's weird. Oh, because I need ball, right? Because it actually okay. But for the tetrahedron with this radius, or maybe another one. But anyway, it's just gonna be like, because it's always gonna be some pi here. There's not gonna be pi in there, so they
Okay.
can't be the same, right? I'm pretty sure.
Is it close?
I'm not sure that this one is the correct one. Where's what is the shape of this one? Oh, this is like complicated way of drawing it. I actually have another nice picture about this one that just shows the intersection and the trajectory, which is also kind of interesting. So essentially, what this intersection shows are what usually people call classical states in the case of deriving them from this quasi-distribution, right? Because we have a quasi-distribution, we can just say, okay, whenever the distribution doesn't have negative probabilities, it's a classical state, right? So and you can show it geometrically. It's just the intersection of that tetrahedron with the sphere. So this is the classical shapes, and the trajectory, because our potato chip is also classical in that sense, but also represents the independent probabilities. That's the trajectory on top of that. And it was kind of surprising that it actually doesn't go exactly on the edge. So it's kind of interesting.
It kind of makes sense because it's the scaling that's the issue, right? So the actual probability of the potato chip here is aligned to the larger tetrahedron, so the angles are going to be more convex.
Well, actually, this potato chip is different from that one. I kind of mentioned before briefly.
Okay.
Like this one is derived from this condition that you start with this. You essentially do the same, right? You have the same shape but inside of this distribution, right? You do the same, but because it's a smaller one, your potato chip is much more bent, right? It's a smaller one than this one. So this is much flatter version because we intersect it with the larger tetrahedron. It's like we had some plot that compares them together, just to see. Like see, one of them is like this. They go through the same point here.
The one that looks more flat, that's sick POVM. The one that is kind of deeper, it's quasi-probability cases.
Okay. Interesting. I mean, it's just a slightly larger tetrahedron thing.
Yeah.
I think eventually, like, one interesting motivation is, like, this geometric approach and analysis to these, generalized, probabilistic description. Like, it provides lots of insight into the meaning of, quantum states and how we can explain them. Block vector is a very natural maybe because, we have learned it and we have seen it a lot. So this is one of those things that I'm still making my peace. Like, when we say block sphere and block vector, is it a good way of representing, like, at least a qubit? It highly depends on, like, God knows how many years, more than 100, years of just seeing this picture and playing around with that. And the amount of literature on these topics, like, no comparison with any other, like, alternative explanation.
You mean like there's more?
But alternative?
Or less?
Yeah.
The most.
Yeah. The alternative explanation, they are interesting. Like, it's just this potato chip, you realize, like, it has a very beautiful geometric description. It's literally the cross section of, a bunch of geometric objects. So they may look more natural. And if there is a generalized, like, probabilistic theory approach, one might be able to reproduce quantum results by just following classical probability game. Like, you do some inference, like, either forward in time or backward in time using your probability theory. Like, does it mean you can recover the whole quantum structure? That's a very strong statement. So
I'm pretty sure you can.
What would stop?
It's not that strong.
What would stop you from recovering it? Like, what do you think would be the?
Oh, nothing. Like, we are exploring that. It's just like, it's basically the whole majestic structure of, like, what we call as a quantum theory. If we can reduce it to these, like, generalized theories, like, that would be very interesting. It's just It would be a surprise, definitely a surprise, but you know, very interesting.
Just a
And
quick
then
question.
what would be
Yes, what would be what?
what would be eventually for any scientist is like, okay, like, you know, besides a maybe bare explanation, are there ways to distinguish them from other approaches? Like, you know, yet
Like
to be
fermion
seen.
mechanics or something? Like, do you mean that type
Yeah.
of other approach? Like, is there?
Like,
is
you
there...
know, if we can test them.
Yeah, bone mechanics is like a completely different
It's
animal.
completely different.
Because
right?
here we don't talk about mechanics, we just do computation. It's just finite dimensional spaces. In order to go from finite dimensional to continuous space, it's like another, it's not a set of problems. It's a complicated problem, but it's not like a something that we don't know how to do. It can be done in principle, it's just hard, right?
So the geometric.
But what I want to get from this kind of perspective from probability theory is just, instead of thinking in terms of quantum computers and how you can construct something useful from doing quantum algorithms on them, think first how we can use probability theory and these concepts of how you can use retrodiction if you could do it efficiently, like how you can do inference, what kind of quantum algorithm, or how classical algorithms with that feature, what kind of classical algorithms can be done, right? And then if you figure it out and you can invent some nice concept that programmers can think of in terms of like these probabilities and how you manipulate them. If they can use them efficiently, then we can ask, okay, now there's a mechanism actually turning this into the quantum computation. So directly, right? So this kind of perspective is maybe useful in order to make use of quantum computers.
Very cool.
To be seen.
Very cool.
Sorry, guys, I also have another, like, you know, meeting, like, you know, that has already started, so I have to drop off very soon.
Okay, cool. I think we can wrap there. Thanks so much for tuning in, and hopefully the potato chips make more sense now. By the way, there is a live stream that Steven's doing today, talking about nestedly recursive functions, his blog. So for those of you interested in that, I would definitely tune in for that stream. Otherwise, yeah, we'll catch you on the next session. There's a few interesting ones lined up next week, but stay tuned to the Discord channel and we'll announce the live streams coming up for that then. Thanks everyone.